Who knows what you might see.
Performative.
Okay. Yeah, okay. It seems to work fine. All right. Hi, everybody. Thanks for having us. We're very happy to be in Venice and excited to see the Palazzo. So I'm Kevin.
Paco.
And together we are Studio ThusThat. We're based in Amsterdam. Now if I click next. Yes. So the presentation today, I'll sort of go through a bit of who we are, a bit about our past work. The microphone is here. Is that fine? You think it'll catch? Okay. So a bit about our past work and some themes that we kind of go through in our work. And if we have time, if you're still up for it, we can talk about sort of the technicalities of the materials at the end. And we brought some little samples, but I actually forgot that we did actually send you some samples, but we have some other ones to look at. So I'm originally from Santa Fe, New Mexico, which is a small little town in the desert in the US. And Paco is from Münster, Germany, in the west. We both met while being at the Royal College of Art, alongside with Flora here, during our master's, the same degree, Innovation Design Engineering, shared degree with Imperial College. And our focus is primarily on exploring the backgrounds and origins of everyday materials. And mostly that has been, up till now, focusing on industrial waste and specifically mining waste. And so before we jump in, I'll just talk a bit about this question that we'll come back to as kind of an overarching question throughout our work, is what is waste? Generally, there's a misunderstanding that we think of waste, we think of kind of the stuff that leaves your house in bags or that you see getting shipped off. This is kind of the end-of-life waste. And to that degree, what Brian Thill says, the author of this book called Waste, is it's every object plus time. That's true to some degree. This is that idea of obsolescence, but every object and every material around us also has a marker, a sort of counterpart, and some trace left behind before it ever made it into your vision or into your hands. This is what we would call sort of before life waste. And that stuff is really quite invisible. We don't really see it. It's not part of our everyday sphere. It never makes it to the public eye. And that kind of waste is inevitable because as much as humans can create order, like the city of Venice, we also create a lot of chaos and disorder. So put in a more elegant way by Katie Soper, waste is essentially these inutilizable remains of human productive activity and consumption. And she also says that this is a defining trait of humans, which maybe the kind of non-human-centric view would actually debate that and challenge that. But basically, this creation of waste is perhaps uniquely human. And an important distinction that she makes here is this idea of it being both a result of consumption, which we're familiar with, right? Waste from our kitchens, but also this productive activity. Right? So we create waste in the production or in productive activities. And one of those things is mining waste. That would fall into that category. We as a studio, we say waste quite liberally, and the word generally gets tossed around quite liberally. In our context, there's many offshoots to this word that include the list of words you see here: overburden, residues, spoils, dross, etc. There's a lot of confusion between the word waste and byproduct, and a lot of companies, but also legislation will sort of challenge what that means and which word we use. We are just going to use waste quite liberally. We just mean anything that's kind of generally considered of less value, that's left behind, unwanted, or even stigmatized. Generally speaking, go ahead if you want to take a photo. There's many words that they use specifically in mining and metallurgy, and you'll hear people say tailings often to just talk about anything that comes out of a mine that is just false, but it's okay. These are confusing words and they're very sort of specific. But generally for us, waste is something in two sides, which one is that it has loss of perceived value, and the other one is that its usefulness is lost.
Yeah, I'll dive into our first project to kick it off, and kind of, I think this project also coined our idea of our mode of thinking as a studio quite a lot. So it's quite a good starting point. And it started in the RCA in our masters in London. And in a nutshell, what we did is we made ceramic tableware from red mud. which is the waste of the aluminum production. And we kind of started this project by looking at aluminum and that shiny metal that we all know, and realizing that it is not mined as a metal, and it has a much muddier origin than what we knew before. So we learned that aluminum originates, or the raw material of the aluminum production is bauxite ore. Sorry. Yes.
Where is the water?
So bauxite ore is this sedimentary rock that gets mined in these gigantic open pit mines mainly, and they're in places like Australia, Brazil. Actually, now that we have a Brazilian here, and also smaller places like Guinea, which is curious because I just read up on it, and Guinea has a quarter of the global stockpile of bauxite is there, and it's a really small place actually. And it's mined there in places like this, and then it gets traditionally shipped to the developed world where energy is more cheap, just because the refining process is extremely energy intensive. And what we get then is alumina, which is basically a white powder, and that is extracted from this red stone, and 99% of the alumina goes to the production of the metal, and other parts go into ceramic industry and other industries. And alumina is then smelted in a thermal process and processed further into this shiny metal that, well, it's not a MacBook. It's probably still aluminum. That we see all around us every day. And in the process of going from this red stone to white powder to then go to metal, we are left with red mud, which is this muddy substance. And it has two problems mainly. Is that it's very caustic, so it has a really high pH value, and it's quite messy. What I mean by that is that because of the process that it has gone through, it was ground so much that it has a really fine particle size. So when it dries up, it gets airborne, it flies around, you breathe it in. It's just not a pleasant substance, and that's why it also is classified as a hazardous waste, which we'll get back to that later, because that is actually really important in this whole discussion of reuse and valorization, because it limits the reuse a lot. And I don't know if I got this correct, but there was an interest. Paulina was saying something about the paper use in the exhibition, that it was usually done with this algae from the lagoon, but that was also classified as a waste, and now there has to be another algae. So a very similar story with red mud, that because it's a man-made material, it's been scrutinized a lot and classified as a waste, and sometimes that limits the use, even though if you look at the performance parameters, for example, there would not be a reason to limit the use. And there's just a lot of it being produced, because for each part of aluminum we produce 2.5 parts red mud, and you can kind of see in that image the relation between red mud and aluminum, and that then yields 150 million tons that are produced each year, and they're left in these ginormous landfills next to the refineries. So in the kind of bottom right, you can see those architectural buildings. That's the refinery, and then all of the ponds around it, that's all red mud. It spans, I think, the diagonal span over the whole waste site is something like 5-6 kilometers, and those ponds are up to 30 meters deep. So if you get an idea, it's just a lot of material that has been accumulated, and it just gets dumped there, and nothing really happens with it, and that then amasses to a global stockpile of 4 billion tons. This was in Australia, by the way. This image is also taken from the same waste site. And even though there is this strange dark beauty in these images that are taken from space, there also obviously are environmental implications. And just to give you an example, like a first-hand example that we witnessed, is we sourced our red mud initially from the south of France in a place called Jardin, which is a town next to Marseille. And interestingly, it's also historically where aluminum production began. So in a way, it's kind of the OG of the red muds, and that's where also the red mud production began. And we went on a site visit there and met with a guy that works for these mining companies and manages the historic waste sites, but also the waste sites that are still in use. But around that region, there are just a lot of historic ones which are disused, but they're still there. And some of them are exposed, and it's just like an open landscape. You can see the red mud, and some of them are remediated, as they call it. And you would think that we're walking just in the forest or on a mountain there, but we're actually walking on 3 million tons of red mud there, which was put in a valley, which I guess the thought was, we have 2 mountains already, let's build a dam, and then we have a big kind of pool that we can fill with historic red mud. So they did that, and they topped it off with 6 meters of topsoil, and as you can see, it worked really well, and actually you don't notice that you're walking on a waste site. But the problem with red mud in this instance, for example, is that it's very thixotropic. So that means that it kind of behaves like cornstarch in water. So it feels solid and hard, but then when you agitate it, it becomes quite liquid. And because of that thixotropic nature, they have to monitor those waste sites really carefully. And the guy that was showing us around was saying that they do that with GPS tracking, basically, of the mountain. So they see how much does the mountain move. And somebody will ask him, so let's assume you see a movement that is worrying, what can you do? And he said the amounts of red mud that are stored there are so big that basically the only thing you can do is evacuate the 11th arrondissement in Marseille, which is basically to the north of the red square. That's where Marseille is. And you just have to evacuate, because if that moves, it moves. And another interesting thing that he was telling us is that for his work, waste management boils down to water management often. And the fact that the climate is changing so much in the last 2 decades, basically, means that all the predictions and all the weather models that they were using to engineer those waste sites are outdated, and actually they have a lot more rainfall and a lot more concentrated rainfall in short amounts of periods of time. That, these waste sites are often not very well engineered anymore, which obviously causes a huge liability for either the government that owns those sites or the companies that still own them. And if something does go wrong, then you end up with this. This is in Hungary in 2010. There was one of the dams of one of those waste sites broke, and the red mud spilled into the neighboring villages, killed 10 people, and just flooded an area of 40 square kilometers. And it's just an obvious hazard to the environment, all the inhabitants of that environment. And while we are quite interested in that aspect of red mud, it's also not the only thing that really drew us into doing this project. And those things were more the sheer scale of looking at this industry that was quite hidden. Like it's very invisible. Like we didn't know about it before starting this project. We didn't know about this muddier brother of aluminum. And then the relevance. So aluminum is kind of considered this material or metal of the future because it's very lightweight, it's infinitively recyclable. All of these really positive aspects that are true. And then when we saw these images from space, there was just a weird contrast between this strange, dark, brute industrial landscapes and the beauty that also is in these images. And it's important to note that we're not the first to look at this space. This guy is Joseph Bayer, who's the inventor of the Bayer process, which is the chemical process of extracting alumina from bauxite. And he already in his early patent mentioned that there is this waste that you create in this process, and that there are certain different use cases how you can use that as a byproduct. He called it probably byproduct. And then after him, obviously, there has been decades of research, mainly into how can we use red mud, bauxite residue as called, as a building material. And for us, what was kind of striking is that there was a really stark disconnect between the amount of research that had been done and the actual real-world implementations that had been that we could see and that we could not see actually. And that we asked ourselves, why is that? Why is there so little implementations of this material in our built environment? And when we started the project, a lot of people asked us, like, you should probably make a brick, because that answers the question of volume, because there's just so much of it. So you need to make a large volume use case and just solve this problem through bricks or cement. And then we did a bit more research and we realized that that had been the approach for decades. And we realized that the problem is a lot more complex and this silver bullet solution will not solve it. And the main limiting factors are threefold, which is the economics, and mainly the economics of scale. So if you make bricks, you'll compete with cement industry and brick industry, which is huge already, and cement and bricks are dirt cheap. Legislation, that goes back to this paper idea of it's a hazardous waste, its use is limited, the logistics is actually really difficult, so you cannot ship a waste around freely. And public perception, which means that people simply are very reluctant to accept a waste-based material, especially when it comes to building their house. There seems to be something in people's minds about my building is permanent and I don't want this to be, I don't want any uncertainties with this. So there was an example for this in Jamaica where actually the mining company that exploited the area for bauxite then built housing for the mining employees from red mud, and people were just not accepting that and said this is probably not safe, we don't want to live in them, and they straight up rejected this initiative, which was probably well meant. And all of these three factors are obviously interdependent, and solving one will not solve the issue. So we thought, okay, what can we as designers and makers and artists then bring to the table that is new, that is not the same as decades of research have been trying to do, and what is our role in all of this? And we realized that the scientists ask performance-based and economics-based questions. So they ask, how can we make these building materials strong enough, and how can we make them cheap enough? And we realized that as designers, we're a lot more free, because we actually don't have to answer either of those questions. Like, as long as it's kind of that tile that is there, like as long as it stays in shape, it's fine-ish. And we also don't need to answer to, like, we don't need to compete with actual, like, cement industry. But we can ask much more philosophical questions almost, where, like, for example, can it be beautiful? Can it be useful? What are the aesthetics, etc.? And we realize that the goal is still the same. The goal is valorization of this material, which basically means bringing new value to this material, whether that is economic or emotional, aesthetic, or intellectual. And we think that these approaches are very complementing and they work well together, and that's why these collaborations that we had with scientists have been really fruitful in the past. So we did not end up making a brick, but we ended up making tableware. And for us it was kind of the contrast of this finesse and fragility with the brute nature of this industrial processes in this industrial landscape that we were dealing with. That was intriguing, and we also wanted to provoke, and we wanted to ask more questions than we would answer, and we wanted people to ask themselves, if scientists say this is completely fine, this is safe, would you then bring it close to your mouth? Would you touch it with your hands? Would you eat from a plate made from red mud, but also kind of ask this question: why is it that we have this need for ever more pure virgin materials? Like porcelain is a great example, that like only because of its purity it has this translucent nature that you can actually like see light through it. And why is it that we long for these absolutely pure materials? And we realized that obviously making tableware won't solve the problem. Like, we're not going to sell enough bowls and plates to solve it, but it might be an appropriate means to tell a new story and to kind of uncover this muddier reality of our material world and reveal something, but also show a more or an optimistic alternative to this apocalyptic imagery of like industry exploiting the planet. And yeah, we wanted to challenge the perception around the material, but both the primary material, like the aluminum in this case, and its waste. And in a nutshell, we use ceramic tableware and design as a means to this end, as a tool to communicate, rather than like problem solving.
Okay. All right, so as we mentioned earlier, waste, we kind of split into this two ideas: one, a loss of perceived value, and then one, the loss of usefulness. So the next project we'll talk about addresses a bit more this idea of usefulness of waste. In this project, we were looking primarily at copper slag, which is, we'll get into what it is, but essentially copper, if we look at copper as a metal, it's a really fascinating metal. It has an amazing history. I urge you to dig into it a bit. It is the oldest metal mined by humanity. There's evidence of it almost 10,000 years ago, which is roughly the same time we started planting wheat and doing agriculture. It is infinitely recyclable. They say that 80 to 85% of all copper ever mined by humanity is still being circulated, which is quite cool to know that our wires are maybe composed of Sumerian copper. And it's obviously very relevant today because of the electric future. So, for instance, a wind turbine has about 5 tons of copper in it, and 10 tons of copper are used for every kilometer of high-speed railway. And this is just in cabling, wires, coils, etc. So the demand is growing very fast. But we're actually running out of copper. The quality of ore used to be, you could find ore up to 40% purity copper. Now that is decreasing, so mining companies are quite lucky if they're able to find anything with around 0.2% copper. And these are different ores, so you have like chalcopyrite is the most common ore. And so there's almost no copper in any of these stones. And peak copper theory is a theory that says that we are running out of copper, and we will be running out very soon. Some predict the next 50 years, some 100 years. Very, very short time span. So that involves like electricity, motors, everything that uses copper. We won't have any more of that. So in the past 10 years, one science paper, for instance, shows that the quality of the ore is decreasing and the energy needed to process this is increasing. So that's actually equals about 8 to 10% of total global consumption of energy is used just in extraction, mining. Not just copper, but just mining in general. That does not include metallurgy. So we are indeed running out of copper, but the reality is we're actually running out of accessible copper. Copper is just becoming more and more dilute in the earth crust as we dig around and kind of exploit the nearest veins. And the reality is also that science keeps catching up. So old smelters used to look like the engraving on the left. Newer smelters look something more like on the right. So as grades of ore continue to decrease, our ability to actually maintain economic viability when we mine increases of ever lower grade ores. So this means that now we have to mine, and we can mine, entire mountains and excavate them just to make wire. So this is La Escondida in Chile. And obviously paired with this sort of digging into the earth is the exploitation of the developing world and cheaper employment. So if you look at the largest mines in the world, it's Chile, Peru, Indonesia, Poland, Mongolia, and in the US, it's on Native American reservation land. So this is the mine that we visited, Paco and I, just before COVID in Resolution, Arizona. Ciao. And this is on Native American land, and they're basically digging out the entire negative space of the mountain above it. It's just creating a negative bowl underneath in kind of like a Swiss cheese format straight into the earth. So, as I mentioned, the growing demand, lowering ore quality, more energy, more unwanted materials, and more waste when you produce copper. So one of these wastes is slag. Slag is essentially, it's literally man-made lava in many ways. It's quite cool when you see them pouring it out, but it's essentially the impurities accumulated during the smelting. So, and it's skimmed off the crucible and poured into these massive mounds, as you see here. And slag is not new. So this is an image that we took in Cornwall, so that you can see across all of the post-industrial landscapes of Italy, of northern France, of England, you'll see slag piles. They have different words for them in different languages. This one's in Cornwall. This is also in Cornwall, just some remnants of a mine. You'll see that's an old mine shaft, that hole in the center, and that green sort of strip on the bottom is basically oxidizing copper, so you can kind of get an idea of how back then, the copper ore quality was definitely higher. Slag is also fascinating because it's used by archaeologists to trace the earliest uses of metals, our earliest productive activity, so to speak. And it's kind of insane to think that we've been making rocks as a species. We've been essentially making rocks for 10,000 years. No, well, not 10,000, less than that, because smelting appeared a bit later. But slag has been accumulating for a very long time. It definitely accumulated during the industrial era, so as you can see in this painting. And it even began to enter the sort of canon of landscape painting. And the slag mounds just kept growing as we entered the age of electrification and the wars. So that is not a mountain, that is a slag pile behind the buildings. And today it's exploding with the age of new devices, electric vehicles, and of course recycling. So recycling is of course a good thing, but it does indeed produce slag as well. 55% of European copper comes from secondary recycled sources, which is great, but it's still producing slag all over the place. And the problem with this slag is it is more hazardous and more contaminated than slag from mines, because it's got all kinds of random metals and junk mixed in. So this is, on the left, is a sort of modern slag pile made from recycling. On the right is a slag pile made from mining at the turn of the 19th and 20th century. So we are now creating new forms of sand and stone made from the impurities of recycling batteries, electronics, and new alloys. And there's still this kind of, I found this article, I just thought it was kind of funny. There's still this contempt for slag in general. So this is the new building by MVRDV in London that got basically destroyed by critics. And they were calling it a slag heap, which I thought was kind of flattering because I like slag. But it's an interesting thing that we still use this word as this sort of atrocity of bygone days and like a slag heap. But we are producing slag heaps all over the place, and it's just this view that it is basically the landscape form of a pile of trash. But actually, for us, slag is really fascinating because slag went through a very high thermal process. Basically, it was turned into this molten lava-like material, and in that process, it's basically changed the composition of the material. I'll go into this later, but it allows it to be used as an active ingredient, as a cement, as an alternative to cement, what they call a geopolymer. And that's just a byproduct of the process itself. And so you don't have to reheat it, you don't have to do things, it's just piggybacking on a metallurgical process, and it's reactive. And this alternative cement, this geopolymer, has 80% lower carbon footprint than regular cement without sacrificing any performance. It's very resistant in ocean environments, like here. But just like red mud, as Paco mentioned earlier, we are definitely not the first people to think of using slag in this way, or to think of using slag in the built environment. Scientists have been doing this for a long time, but there's also evidence when we were visiting the mines in Cornwall, you see actually in all the structures of the mines themselves, the sort of ruins left behind, they have slag stuck in them because they were using slag as aggregate and as rocks in the actual built environment already. So the idea has always been there. People have kind of always seen slag and been like, oh, maybe I can use it. But today, in terms of large scale, there's very little use. Most of the slag use is in sandblasting, which is just awful because if you think about it, then you're just mixing it with toxic paints and all kinds of other things. They use it to clean ships because it's very abrasive. And so then you have a hazardous waste that's also contaminated with a million other things. So it's not great. And so the researchers in Belgium at KU Leuven have been looking into the ways to use it in a positive manner. So to actually offset needs in other industries. And that's where the geopolymer research came up. So we were invited to work with them and a copper recycler in Belgium to basically look at their research and see how we could translate it into the perspective of a designer or maker. So we spent about 2 months with them, and we studied their research, studied the material, and tried to see how we could translate it out of the lab context and showcase, basically what had always been stuck in little formats of cubes for compression tests and things like that, and try to see, can we do something else with it? So for instance, this piece was, looking at the castability, the machinability, but also playing with this idea. They talk about the thermal resistance of this material often. So we decided to try to join slabs together using molten copper, and just pour molten copper directly into holes and just join it with metal as like a glue almost, or a mechanical joint. Works great. And with cement, if you had done that, it would have probably just exploded. So this piece was kind of playing with the rheology of the material and how it flows. So if you slap the material, it kind of gels out a bit like cornstarch and water again. It has this thixotropic nature, or the particle size and the different sort of way that it packs together. So this piece, we actually just dug cavities into the slag and cast the geopolymer mortar directly into those holes. So the slag here is the binder, the filler, and the formwork. So it's all made using slag. This project was essentially demonstrating the value of collaboration with scientists and playing off each other's strengths. And it really was a back and forth with them constantly, a very high-paced project. So there's some pieces, that were not particularly our proudest piece or really in our style, but the point was really to speak to what the scientists were researching and speak also to the crowd. Because at the end, we held an exhibit at the factory where we invited factory workers, construction industry members, sort of metallurgical members, architects and scientists, and they all came to sort of look at these pieces. And alongside the perimeter, you had all the different stations that was showcasing the different actual PhD research going on. And then in the middle, you had kind of pointers of how that sort of translated. And it was just to spark their imagination and get them talking, and it worked really effectively. And so since then, we have continued our work with slag. So we used from some of the techniques that we actually were investigating there. So one, I mentioned that thermal resistance of the material, its ability to withstand thermal shock. And so now we've been playing with this idea where we actually melt powdered glass directly onto the surface of the concrete, essentially, the geopolymer concrete. Again, not possible with cement. So you basically take a piece, put it in a furnace, pull it out a few minutes later, and it's done. And we've been returning to some of our the earlier uses of copper and sort of how we can integrate copper back into the pieces as well. So this is Michael Johnson, who's a coppersmith in Cornwall. And coppersmithing was a huge art back in up until the late 1800s, and then just totally vanished. And so we've been playing with this and using a more coppersmith technique on the metal and bringing the metal back with the waste and trying to join the two to tell a story about both. And so you see these kind of organic monoliths that echo a bit the slag heaps and this kind of new organic texture to it. So yeah, different pieces. Yeah. And the reason, and so we've called this series of explorations of copper slag, we called it This is Copper. And the point of this was trying to contextualize and redefine the material copper that we take for granted. So what we're trying to say is that copper is not just this metal, it's this whole gamut of materials from the waste, the stone, the chemicals, all of that is the story of copper. And we forget that often, and we just think these materials appear out of thin air. Okay, so some thoughts to consider. Are you guys, is everybody good? Yeah, on it? Okay, we can take a pause here. Can you? No? All right. Okay, so back to the question of what is waste. So in a way, waste is an admission of failure. It's in some way some failed system of production or failure to reach this perfectly homogeneous material like aluminum and copper. But interestingly for us, the failure within waste is actually what allows us to use it in the case of red mud. So the only reason why we can use red mud as a ceramic is because there's some alumina in there, but it's supposed to be a waste of extracting alumina. But the inadequacies of actually extracting it, so there's about 18% alumina in the waste. So their inability to perfectly remove it is actually what allows us to use it. Just kind of a neat little side note. But it's also the admission of failure, or the thing that this like sort of uncanny, unfriendly reminder of waste that makes us feel like we did something wrong, is maybe why we keep it out of sight and out of mind. Because again, it's this reminder that where we make order, we make magnitudes more chaos or disorder. I guess the way we can see it is that for us, this idea of the extraction, or the architecture of extraction, is what Tom Chivers, who's this author who wrote this book called London Clay, he would call it an archaeological dig in reverse, because as we keep digging down into the ground, we also keep piling things up externally. We build layers in our world, and this is kind of sedimentation of nonsense, just building up over time. But this nonsense, this chaos, is obviously relative to how we perceive it. So an example is this waste site in California, in Boron, California. It was a boron mine, was just looking like this for a very long time, of just waste piled up. And now it's the site of green gold, lithium. They found out that there's a lot of lithium in this waste, and it's now the largest lithium producer in North America. And so they're mining their own waste, and they're making a lot of money off of it. So again, chaos is in a way, or waste is relative to how we perceive it. And a great example of that is also fluoride. So fluoride was actually initially, the benefits of fluoride were first ironically noticed in Italy, in Naples in 1902. And its first effects were noticed on a town, at a town scale, in the water, ironically in Bauxite, Arkansas, by the director of Alcoa Aluminum. So it was actually weirdly an aluminum company that just happened to see it in their water and be like, well, all our workers' teeth are doing great, but they're kind of brown, and that's strange. And they passed it on to some researchers. And then in the 1940s, the researchers who had looked at the value of fluoride on your teeth actually managed to implement it in Grand Rapids, Michigan. But fluoride originally is a waste of agriculture. It is an industrial waste. And they were just looking for ways to use it because it was stockpiling, and they didn't know what to do with all this fluoride. And they figured out that they could just put it in our water. And they called it the greatest miracle of health of the 20th century, because it got rid of all of our cavities. So that's a good example of how industrial waste can turn into something totally different. But there's obviously a contentious subject. A lot of people hate that they put fluoride in our water. So a different question is, what is exactly the difference between a mine and a quarry? They're basically the same thing. But a mine, when we say mining or a mine, we think of kind of devastation, chemicals, and this like Anthropocene vision. When we say quarry, we think of like stone and sort of vernacular architecture. Oh, that's nice, like stone quarry. But essentially they're the same thing. But it kind of comes to this tension that Paco talked on, is this tension between materials that are touched by man or modified by mankind, and then those that are more natural, perceived as natural. So a good example, for instance, is waste has to go through a lot of certification and legislation, and issues reach certification, and is scrutinized based on its performance, its composition, its hazardous nature, how it's transported. Whereas things like granite is just like, they just go smoothly. And so people give us a hard time often, or they kind of try to attack us on the radioactivity of red mud, because indeed some sources of red mud can be radioactive, but most sources are not at all. They're well below household levels of radiation. But granite is quite radioactive, but it doesn't get scrutinized to the same degree. So we just don't care so much about the natural materials in terms of how we scrutinize them. And this question is taken a bit from Antoine Picon's essay of Rust to Ruin. There's this weird tension we have with rusty landscapes versus ruins. So when we look at rusty, sort of decrepit buildings on the outsides of cities, it's what he calls a technological landscape. It's this reminder of failing human ingenuity, of things just not working out. I think we just, we messed up. And it brings us this anxiety. Whereas when we see ruins, we think of this kind of testament to human ingenuity and how great we are, and it's just been consumed by time. Sorry, if you, okay. So ruins in many ways speak to our memories, the past, right? It's this sort of incomplete vision. And the interesting thing is, Ken Warpole puts it, is that they demand to be viewed whole again, as opposed to a rusted landscape, which is just decrepit and ruined, or decrepit and in chaos. A ruin actually demands to be viewed whole again. Can you read that all right? Yeah, right, yeah. But in many ways, ruins speak as much about our past as they do about our imagined future. Because, I mean, I would say I agree with this, that when we contemplate these sort of old castles and things, they kind of, in reimagining them as whole, we also project ourselves into a new future. And this is not a new thought. So the Renaissance, obviously, like Filippo Brunelleschi, went to Rome to study the ruins of Rome in order to develop these new ideas of perspective, which eventually led to, you know, the great creations of, for instance, the Florence Cathedral. That was stemmed from looking at the ruins of the past. But waste, unlike ruins, doesn't really allow this perspective gaze forward. It just stops. It's a total dead end. It's rusty and it's stigmatized. And we've played with this thought before. Paco and I have talked about this before, this idea that perhaps there's some part of us that almost keeps wastelands and keeps the idea of this apocalyptic end. We preserve it in some way because it's almost tempting. And it comes to this idea of when people gather to watch bridges get demolished, or when we slow down at an accident on the highway. In some way, there's this kind of temptation that comes to it. I think it was Kierkegaard who talks about vertigo as this idea, not so much that we're afraid of falling, but that we project ourselves having fallen and we're afraid of the desire to fall. It's kind of this weird, like, oh, I kind of want to jump, and you recoil in fear. So maybe there's some sort of temptation, and this is pushing it a bit far, but it's, in a way, you can see like waste sites, the wasteland, as this, in a way, the skull of the Vanitas paintings. It's this kind of weird reminder of our eventual end. And this is kind of a joke that maybe that actually is a slag pile in the back of the painting. But really, it's this. There's something fascinating about ruins in contrast to waste, because there's a multiplicity of ways to see the ruin whole again, from the past and to the future. But waste doesn't afford that. So maybe what we're trying to do in our work is actually try to see the wasteland as not so much this anxious landscape, but as something that allows us to imagine it in a whole new way. So in this right image, this is just little pieces of slag geopolymer that we formed, and we electroformed waste copper wires back onto the slag. So in a way, we're reversing the production cycle. Usually you have the stone, the waste, and the copper. Now we're saying copper comes back onto the waste, and you're creating this new form, this new ore, if you will, a new stone. And we're, again, not the first to do this. Nature has already been doing this for a long time. It's been showing that wastelands can be these really fertile spaces of possibilities. So this is the Matsukate mushroom, which sort of thrives in this kind of in these landscapes that have been ruined by humankind. And obviously tackling this problem is difficult because we try to keep it out of sight and out of mind. Both as consumers, we don't like to think about these things, but companies, mining companies and everybody else doesn't really want you to know that there's huge piles of waste somewhere. And there's, I like this because this idea of preserving the wasteland out of, and sort of almost keeping it safe. You see it in LA. This is the Brea Tar Pits, which are actually a waste, a mining waste site. People think it's this natural bubbling pool of tar, and it's like this cool place, but actually it was an asphalt mine. And these are just the waste like pits left behind. And we preserve it and keep it in the dead center of the city, this like nasty, bubbling, smelling thing. And we just preserve it as this like weird museum in a way. Waste sites, because of legislative barriers and things like that, are often monitored and kept and sort of preserved in much the same way. So a good anecdote is this waste site in the south of France that they tried to remediate, and the locals actually protested because they said it had become part of the landscape and they liked it. So it's actually considered now part of the heritage, the local like patrimonial heritage of the region, which is super weird to sort of preserve your waste site like that. Yeah. And there's more to there's actually a really rich story behind that building too. It's a really cool, you should dig into it. It's called Vitrolles in France. There's a really cool architectural nightmare of a story. That building is still cracking and moving because it's built on a waste site. Adorno sees this, he kind of connects museums to graveyards because of this idea of how we preserve and we dissociate things from the viewers. we kind of separate this relationship. And in many ways, that's what's happening here. By putting things in waste sites and keeping them out of sight, out of mind, we just forget that everything has this counterpart and this trace left behind. So our role really becomes trying to put wholes together again, and we're trying to connect things in new ways and show what they are, where they come from, where they came from, and where they could be going. In a nutshell, storytelling. And there's this designer, Thomas Pausch, who calls it mythologizing, which I like a lot, saying that we really, designers shouldn't be afraid of this idea that we do have to create myths and stories. You know, we're not like, a vase is not going to save the world, but you do have to create a myth and start it rolling. And again, the same author who wrote that book called Tom Chivers, he says, and I love this line, for all history is the history of waste, and what was left behind, excreted, discarded, or lost. You see that archaeologists are always digging through waste piles, because in the end, as he puts it, these are the things we'll be remembered by. So that is it. There's technicalities to our materials that if you guys want me to go into after, we can do questions now. We have little things, but you kind of have some samples, but we can at least start opening these because they're all wrapped up. But if you have questions now, before, or would you like me to just go into the technical details of how these materials work? If you have questions now, just throw them at me.